physicists are kind of indoctrinated that every problem is harmonic oscillator, but I'm totally embarrassed when I actually listen to what I say when I'm trying to edit these videos. So I will stop now and teach you real stuff instead of just windbag. So here we go. Today's lecture and the rest of the course is my unending quest to be relevant. This is a pain that every theoretical physicist, especially theoretical physicists like me, suffers from. And one of the things that most of our graduate students will have to do, hopefully 2/3 will be experimentalists of some kind, observing nature and reporting on what they see. And it's almost always a statistical exercise because all measurements are imperfect. And when it gets to be subjects like physics in biology or astrophysics, statistics is extremely important. For example, if you are, as Professor Ignazia Taboada does, counting neutrinos on the South Pole, the neutrinos that you want to count come very rarely, and you have to be sure that they're statistically significant. So I will go through some basic definitions and notions that you will always encounter when you have to deal with statistics. Now, there's always a secret agenda, so it turns out, one more time, it's matrices and the stuff we did in this course, but now it's called probability or experiments or statistical analysis. If you have some data set or your theory is producing data, the simplest measurements that you can do is to look at everything you have and average over it. We did this already in group theory. So for example, we call fully symmetric representation under any finite or compact groups. It was averaging over all possible states. So when you average, there are notions, all of them have many names because almost any field of chemistry, physics, mathematics, engineering has to deal with this. So here is a notion of exact mean. Exact will mean that what theory predicts as opposed to what data gives you. It's also called expectation. And probability is called its expectation, expected value. And they say if we are looking at a variable, random variable called A, this stands for expected value. And we'll do it first in one dimension. If you have something that depends on where you're measuring it and how often we get a particular value is called probability. So this is called random variable. In quantum mechanics, statistical mechanics, this is often called observable. And this function here is called probability. Measure or distribution. And we assume that our space on which the states are defined or measured is a continuum when we define it. So this integral is over the whole manifold in the continuum. It could be that we have just finite number of slots or boxes and we are measuring likelihood of various outcomes. In that case, this sum integral is actually a sum observable on a particular discrete state or configuration. I'll call it pi. Has some value, and it shows up with what's called weight or probability that something will happen. And this is how we define a mean on discrete set of values. And for this to make sense, we have to normalize probabilities. Which means if my observable is 1, no matter what you say, I say 1, then the expectation value or mean or average of 1 should be 1. That's definition. Normalization, in other words, this integral here, or this sum, should add up to 1. So that's a mean. Once you've defined a mean, the next thing that is more or less natural is to find a moment. And that means I just take my observable, like the temperature in Chicago at Lakeshore Drive, and I raise it to power. And then I average that number over a whole year or millennium or whatever. There are lots of things to say. It's called kth moment. You'll see in a while why it does make sense to do this, but right now it's a little bit arbitrary. The first one we know, that's what we call mean. Now, when you look at the second one, it's actually more sensible to define something called central. Because if you know the mean, you're really interested in how things vary around the mean. So it makes more sense to center your variable at the mean value, subtract its actual value from the mean, and raise it to power k. That's called central moment. The most celebrated central moment is the second one. So if you take your random variable or your function you're measuring, temperature on November 3rd, and you subtract Chicago mean temperature, and this, just that I'm saying this tells you all perils about statistics immediately. That's called variance. Now that's easy to evaluate in terms of moments because I just square this out. So I look at the expectation value of this guy squared minus 2 times this guy times the number, the mean, plus the mean squared. And I average it. Now this is something that we have to either measure and compute. So this is the second moment. This is just a number. And the expectation of A itself is that thing. So that's A squared minus 2 plus 2. So I get minus 2 squared. Now, if you make your living as a probabilist, what they say is expectation value of A squared. Remember, that's really just the case moment, equals expectation value, this guy here. But now we have to move the mean squared, so they say expectation value of the second moment is the mean square plus the variance square.
Isn't that negative over there? Where did the negative go?
It went, I took this to that side. Then,
Okay.
expectation value is that.
Yeah.
Sigma is here, and mu is this thing. Now, positive square root of variance has a name. It's called standard deviation sigma. And the way I memorize what sigma is that when I look at some probability distribution that's peaked and looks vaguely like a Gaussian, or maybe is a Gaussian, then its width is 2 times sigma. So that's roughly, if we had a variance, this guy here, we take its square root, and it's half of the width of the thing. When you go to higher dimensions, you'll see why this 2 shows up here. So now that you have a standard deviation, of your distribution, then you can define something called standardized. And standardized moment says, well, if I'm measuring a central moment, let's divide this by this standard deviation to power k. If A is measured in degrees Fahrenheit or kilograms, so will sigma be in the same units, because whatever unit on this x-axis is, sigma will have it. So this is a dimensionless, designed in such a way that the second moment, standardized moment, is 1. So if I want to look at the things under the different scales, this is often convenient, and this object is invariant under translations, because if I change A, go to A plus C, where C is any constant, so I decide, measure it in respect to absolute 0 rather than to freezing point of water. So it's invariant under translation. And it also, if I change my units, so instead of measuring it in Fahrenheit, I multiply it by a correct number here to get it in centigrade. That's just a linear rescaling. So in some sense, this is a nicer way to describe deviations from the mean, their powers, because this is a dimensionless version. It's also very easy to go to higher dimensions. So suppose we have a multi-component observable. This word observable is often used in quantum mechanics, but you call it anything you want, your random variable. But multi-component means I'm measuring, for example, I'm measuring velocity of fluid in 3 dimensions. In general, my problem has d dimensions, so measuring various components of something. Then we might be interested in whether the, moving to the right and moving straight is correlated or not. And to study that, you define second central moment, which is I measure the deviation in direction left. I multiply it by deviation in direction up. So these are some numbers, and then I average over all possible values. And that's called covariance matrix.
So my question is, how can I intuitively see that that gives me what I want in terms of the covariance?
Yeah, the simplest question is, we'll test all this idea on Gaussian probability distributions.
Okay.
And then we will measure, I'll try to argue that when you talk about probabilities, you want to measure everything with respect of Gaussian possibility. As I will argue, Gaussian distribution is the minimal information distribution, the simplest of all possible distributions. And these moments are measuring deviations from that. But this particular thing is now called multi-variate normal distribution if we're only keeping information about the means and about the covariance matrix. And we already know everything about this. We have done this a number of times. This is a symmetric matrix. If I interchange I and j, nothing changes because I'm integrating over all states. This is a strictly positive matrix because, you can diagonalize it and you know how to do that. And what this matrix has, it has eigenvalues which, to be in agreement with our convention for single, not multi-component distribution, should be called sigma square I, and their number is the size of the set. And they have eigenvectors, which I can decide to make unit eigenvectors. Their number is, again, the dimension of this matrix. Now, because it's symmetric matrix, what this really means is that when I change coordinates, I'm thinking of an ellipsoid. In one dimension, I was thinking of distribution, whose width was sigma. So sigma is a semi-axis of distribution. That's why there is 2 sigma here. And it's concentrated within this region, and it's, of order E right there, and it's rarefied outside, has small probability if I think of clouds of points. Now I think of an ellipsoid which has axes 1, 2, 3, and we make this unit vectors. So then the size of this axis, or this idea that I'm looking at sigma away, now becomes, in every direction, this ellipse, it has a size of sigma. So this is sigma 1. It's that long, that thick. And, this is sigma 3 here, and that's squashed. So it's centered around its mean, and it's spread out like a cigar. And now this has all the names you've already seen. In neuroscience, you've always seen they talk about PCA, which means principal component analysis. In fluids, they mostly talk about something called POD, proper orthogonal decomposition. The typical thing is you have some turbulence, you look at it, and you find out that, let's say, velocities are concentrated around zero, but they have some spread, and you're trying to describe it, so you use POD. Now, we know these are just special cases of something we did a long time ago, singular value decomposition. And that's a wonderful thing. Any array that you can put in a matrix, you can find where, in which direction there are big numbers, big entries in this matrix. And just for a good reason, you always have to add some dead old man. So there is Karhunen. Now you probably don't speak Finnish, but Karhun in Finnish means bear. And Löwe, and a Swedish thing, same thing has a fancy name. It's called Karhunen Löwe transform. And there might be more name for the same thing. I don't know. These are the ones that I've run into myself. So going back to one dimension, what we are discussing is lots of numbers because k can be 0. That's a trivial case. Expectation value of 1 equals 1. It could be 1. It's called mean. It can be 2. That's related to variance. But it can be 3, 4, 5, 6. It may infinitely things. So whenever you have such a thing, it's always natural to go to generating functions. So here is what we call moment generating function. Take expectation value of our old friend, which always happens whenever you have a linear problem. You either have sine, cosines, or exponentials. So take expectation value of exponential of a evaluated at every point, multiply by parameter. This parameter is just a parameter. I'm calling it beta because in statistical mechanics, this is called inverse temperature, but that doesn't matter right now. And, expand, you have a function. It could be even multivariate, but it's simple in one dimension. You expand it as exponential, always expanded by Taylor series. And then average. So this indeed is a generating function which contains all the moments you would have wanted to do. But there is one thing that you might find objectionable. What this thing is computing is these moments, but we gave up on moments very early on. We said, it doesn't really make sense to look at moments. We should really look at central moments, compare things to the mean and see how they're distributed with respect to their mean values. You prefer central moment. That's achieved by looking at something called cumulant generating function. And that guy is defined in, again, we're very familiar. Whenever you have exponential, its inverse is logarithm. So let's take a logarithm of this generating function here, or expectation value of exponential of our variable, and expand that as we always expand functions. Now, logarithm starts with 0 because logarithm of 1 is 0. So we start with k equals 1 to infinity beta k And then we have to do a calculation, which I'll guide you through very quickly. And we get some coefficient here computed for expectation values. And this will always have a subscript C as opposed to this guy without subscript. And this is C, which stands for cumulant or for connected. I won't be able to really explain why this is called connected. For that, you have to take a good statistical mechanics or field theory course. So just trust me, that's what it is. And how do I compute these guys and why do I do this? First thing, suppose that, this averaging is pretty boring because when I look at expectation value of kth moment of observable, suppose that this is just the mean to the kth power. Then what happens? The logarithm of exponential expectation value is now simply logarithm of e to the beta expectation value up in exponent, right? Because taking expectation value just shifts it into this function. Now, this logarithm, this is inverse of a function we now have to do. So this is beta A. So what this cumulant generating function says, if there is nothing interesting going around the mean, so all the moments are trivially related to the mean, then this expansion has only one term. It says if you know the mean, you know everything. If you, in light of that observation, think what is AK connected, if that's not zero, this is teaching you something about fluctuations around mean. Y log. Let's find out what this series looks like by computing few terms. And the moment I start, you know how to compute as many as you want, especially if you master Mathematical or any algebraic language. But beginning you can do by hand. The usual generating function is I expand this as a series. There is a first term, I take its average. Then there is a second term, I take its average or expectation value. And this goes on for all the terms. Now let's take a logarithm of this. What's logarithm? The first term is 0, because logarithm of 1 is 0. Then I have to take this whole expression. Then, it's logarithm. So logarithm is the sum over 1 over n variable to the power n. So the next term, and there are some minus signs having to do with logarithm. So next term shows up as minus 1/2. Whatever is here squared, then there's a plus 1 over 3. Whatever is here to the power cube. So that's just algebra. And we want to rewrite this in powers of our parameter beta. There is one term that's linear in beta, that's this one. From here, we have a term that's quadratic in beta, and so on. Now, from here, we have to square this thing. So we get beta square, I square from here. Then, this is give me beta to the 4th, so let's ignore it for a moment. Then there are all these cross terms. There is plus 2 beta times beta squared, that's cube. There is a half coming from here. There's expectation value and expectation value of the variable squared. Plus things that are higher order because, everything here is at least beta to the cube. So the result is we get beta to the alpha, expectation value, plus here we have to, there's a minus sign. There's beta square over 2 for both guys. And this multiplies second moment minus from here, mean squared plus. In other words, the first moment, connected moment, is the same. Mean of the function or mean of connected one is the same. But the second one is actually the correct thing that we like, which is it compares square of the mean to the second moment of the function. And in the same way, you can get as many terms as you want to. So there is no problem of generating cumulants. It just, you can express them in terms of moments, and those you know how to compute. So to summarize, cumulants are generated by taking logarithm of the generating function for moments. We expand them as we usually expand functions as Taylor series. This you always have to remember. That means you're looking at cumulant. Now, the first cumulant, that's just the mean. In other words, cumulant is same as expectation value, same as mean. Second cumulant, just variance. Now we can define higher cumulants, and they're all important, and they all show up in statistical analysis of data. The third one is when I look at the distribution like this one, I've drawn one that's symmetric, but suppose that this was lopsided, so there was lots of stuff on the left-hand side and less on the right-hand side. Then when you look at expectation value of x, of this random variable, you get a non-zero answer for the q because what's negative and what's positive with respect to the mean doesn't cancel. So the whole thing is q. So that's what the third cumulant measures. For example, there are more old people than young people in Japan, or more young people than old people in Kenya. Doing same calculation I just did, very easy to do by hand. If I look to the computed cumulant, find out that this is just really the third central mean, and I can express it in a way I usually express things. I compute third moment, then I have to subtract from it because there's a cube. It'll turn out I have to look at the second moment and mean, and I have to add to it mean to the cube. Now suppose our distribution is symmetric, but it's kind of flat here, then it takes off, and then it's flat at the top. So that's obviously not a Gaussian, but you find such things in experiments. That's measured by the fourth cumulant. I won't write it, but it's in the notes. And that has a name from Greek. I have no idea what it means anymore. Called kurtosis. So that's, you'll run into. Question, why are cumulants better than moments or any other kind of weighted average of higher powers of the thing? The answer, and it's deeper than it sounds right now, if the distribution, probability distribution is Gaussian, then it turns out, simple computation, that cumulant for every power larger than 2 vanishes. So that's easy to check, but Sarah should ask, why Gaussians? So why did they pop up again? And that is a deep, really deep answer, which goes to foundational statistical mechanics and many other things. And today, quantum computing and big data and all other buzzwords of the moment. The answer is Gaussian has least information. So what's this information and why should we be mindful of it? So, it's been with us since the invention of steam engine under various names. And modern name was given by Shannon. Shannon was, let's say, electrical engineer in Bell Labs. And he was trying to understand, the quality of signal. Let's say Morse code you send across lines, transmit. And, how much information, how much meaningful stuff is really in the signal you're sending. And he called that thing information. Now, once you get hang of it, you can redo everything you know about statistical mechanics, if you know anything, in Shannon language, and people love doing that. Rightly so. He says, if I have a probability density, let me define entropy, information entropy, to be simply, I take my probability density. Imagine, it's something that has to integrate to 1, has to be positive. So I can take a logarithm and, it has to integrate to 1. Almost every place should be less than 1. Logarithm of a number less than 1 is negative. So let me put minus here and compute the expectation value of this thing. And to write it exactly as a formula, it means I have a probability function. And for every value of x, I have my observable, which happens to be logarithm of the probability function. So this is probability density. That means that, this combination here is probability. It's a number. And now you ask yourself, why is minus log at any site? Why is that information? Shannon reasoned in binary because that's a natural thing when you're sending code. You either send 0, nothing, or send 1. So you have 2 digits. It's the correct basis. So for example, if I take rho of x at some particular x to be a very small number, let's say 2, because I either have 0, 1 bits, so that's a natural basis. Binary is the basis to express the situation, to the minus 6. Then it said, well, it takes minus log of 2 base 2 equals 6. It takes that many binary bits, digits or bits of information to describe or even start describing the density at that point. What Shannon entropy is, this thing here, is expectation value of information. It turns out, of all possible probability distributions that you can ever write, Gaussian is the one that contains least information. So it's singled out. So the fact that we're comparing when we are describing this cumulants, we're really comparing the distribution that we have to what it would have been if it was just a standard Gaussian distribution. This is the natural measuring stick to everything, and that's why Gaussian shows up all the time. There are many other arguments, but here is one that is statistical in nature.
I think the reason we use Gaussian is highly tied to the reason of the proof of the one of the most important theorem in mathematics, the central limit theorem.
Correct.
So I think that's the reason, because as long as you take enough measurements and you can basically take small groups and average those groups, if you have enough of them at the limit, you'll get a Gaussian distribution, which is quite remarkable. So I think that has something to do with it.
Yeah. I mean, it's more or less remarkable. That argument that you just mentioned, I could have done, it goes via binomial theorem and it goes via Stirling numbers and stuff we have derived in the course. What it says is that whenever I have a smooth distribution and it's around its center, it starts as a parabola. And whenever I have a smooth and narrow distribution, I will only be able to measure this central part, this parabola, and that's how I'll get a Gaussian. And then there'll be fine corrections to it. And depending what limit you take, the fine corrections, are harder and harder to get in eventually. So that's as you say, central limit theorem. That's one way to do it. I decided to go a different way here, but I agree with you. That's one way to understand why always Gaussians. The first thing away from constant, which is symmetric under inversion, is the second power. And anything raised to the second power is called Gaussian. That's one way to get there. But I like the argument I'll try to give you now. The naive limit only pulls out, as you make more and more measurement, your distribution gets more and more precise. You're probing closer to the mean because that's most likely thing to happen. Mm-hmm. And, around the mean, you get more and more precise estimate of the curvature of the distribution, which is called sigma square of its width, or whatever you want to call it, of the Gaussian. And if you only think of that, everything becomes Gaussian, which is, a curse of much of what experimentalists sometimes do. They say, well, it looks noisy. I keep throwing stuff at it and I'll fit it and I'll get a Gaussian and I'll publish it. Now, it turns out that in many systems, this is very true of chaos and turbulence. All the important information is in higher moments than the Gaussian, and they're harder to get unless you take the effort of getting it, because you have to measure more about distribution than just its top. So all the physics consists of getting the other cumulants to uncover that the process is not just random, but there are correlations in the things that happen.